Okay, guys, this is Mr. Gloria. Hey, we've been doing this packet on getting faster, positive acceleration, and we've covered, we've kind of covered, I believe, up to page 3. We've got a few more pages to do, and we're going to do kind of page 4 today. And so make sure you have your packets out, and you're on kind of page 4. You might find a calculator kind of handy to have out too. And let me kind of get over there with my Word document, and let me kind of get a little bit of a screen here. And so we said the how far equation represented delta x. That's our displacement. And delta x, a delta, remember, means a final minus an initial position. That's our displacement. And that equals to 1/2 at squared. This is our how far equation. But I told you last time that we were going to have to maybe modify this a little bit, and we have to make a modification to this equation. And let me kind of show you why we might have to do this. And let me kind of page through here. So, if we kind of go back to this first example we had on page 1, we had this car accelerating at 10 meters per second. So we had we kind of had a slope that kind of looked like this, right? That we had these points. I didn't draw a very straight line, I'm sorry. But we had this car that was getting faster by 10 units of speed every second. That's kind of what we had on page 1. I want to make a small change though to this idea, and let me kind of erase what I just did. Let's say let me ask you if you've ever done this. I bet you have. Let's say you're coming up to a stoplight and you see it's kind of red in front of you, and you kind of anticipate the stoplight turning. Do you know what I mean by that? Like, you see it's kind of red, so you kind of slow down, but it looks like it's about ready to turn green. Um, and so you get up to the intersection. Your car's slowing down, but it hasn't stopped yet. And then the light turns green, and then you keep moving. So you never really stopped at the light. You anticipated the light turning, and you kind of slow down in anticipation of the light turning, and you ended up then uh, being able to go because now the light is green. So you really kind of anticipated the turning of the light, turning of the stoplight. See, like on page 1, in page 1 basically we're at the red light, our car stopped, and um, and then once the light turns green, we leave and we start accelerating from a resting or initial velocity of 0. So what I'm saying now is we're at the red light, our car's still moving, we've anticipated the light, so our initial velocity now is not 0. So let's just say we had maybe an initial velocity. We started the stopwatch. We had an initial velocity of 10 meters per second. So at the next second, we're now traveling 20, and then 30, and then 40, and then 50, and then 60. So do you see then we still have the same acceleration. So our acceleration is still 10 because we're increasing my speed 10 units every second. So do you kind of see how this graph then is a little bit different than the graph we had before? Let me put on what we had kind of before. And so what we had before represented this. Our initial velocity was 0. So we've shifted our graph up a little bit. But you might say, well, big deal, you had initial velocity. Well, it is a big deal. Let me kind of show you why. And let me go ahead and kind of erase, if I can, let me kind of erase those points that we had. Maybe, yeah, there we go. And let me get maybe to a new color here. Well, we want to really create a position time graph. And we said then a position time graph can be constructed from the VT graph by taking areas. So do you see now? Our areas look a little bit different than what we had before. What we had before were those triangles. If you want to look on page 2, you can. We had these triangles. That's what we had before, but now we also have this little square, this little rectangle. So this delta x that we have represents really now two areas. Area of the triangle plus then the area of this little rectangle. Okay, the area of the triangle plus the area of the rectangle. Well, we know then that this triangle really is 1/2 AT squared. Okay, that's what we discovered on page 2. But is there a symbol or a symbolic form that we can have for this rectangle? Well, this rectangle, look, what the area of the rectangle is the base times the height. See, the base then represents t, right? Well, look at the height. It's vi, right? It's 10. That's what my initial velocity was. This vi we said was then 10. So that was the initial speed I had when I anticipated this turning of the stoplight. So what I can do is write then vi t, and that represents the area of the rectangle. This represents the complete. Let me kind of give it a big old circle here, and I kind of get a different color. That really represents the complete how far equation. Do you see how it's kind of different than the equation we had before? What we had before was just delta x equals 1/2 AT squared. And that works if the car, the object, has an initial velocity of 0. And that's kind of what we saw then on page 1 and 2 of the notes. So this more complete formula factors in what can happen in a more realistic situation, that a car could potentially have a velocity when it starts to accelerate. So we have this term that we had before, plus we have this new term. Okay, well, let's see kind of what sort of difference that makes to my position time graph. So let me go ahead and put on what we got, what we had before, and let me maybe do a different color. So if you go to page 2 of the notes, we said we ended up getting kind of a parabola, a top opening parabola, and the car ended up getting to 125, right? So this was our parabola. This is the parabola we got for page 2 and pages 1 and 2. A car that's just accelerating, right? There's no initial velocity. Well, now let's kind of do the same thing. So at 1 second, so let's kind of write our formula here. So 1 second, where's the car? Well, our acceleration we said was 10. We're going to put a 1 here. We're going to square that. Plus we have an initial velocity of 10 times 1. So can you kind of figure out what that is? So we're going to have 10 times 1 times a half, that's 5. That's our initial 5 plus 10. So we're really now at 15 units of distance. So let me kind of change the colors here. So now we're here. So without the initial velocity, we ended up going 5 meters, but now we have to add an additional 10 to that. So this would be then 1 comma 15. Okay, now what about at 2 seconds? I need a little more room to work, so I'm going to mouse down here. What about 2 seconds? Delta x equals 1/2 times 10 times 2 squared plus 10 times 2. You see how that equation works? So that's going to be, 4 times 10 is 40. Half of that's 20. That's where we were before, 20. But now we have to add an additional 10 times 2 or 20. So now then I'm at 40. Okay, so right now then I'll be here at 40. Okay, so we've got to do for 3 seconds, 4 seconds, and 5 seconds. So we can do the same thing. 1/2 times 10 times 3 squared plus 10 times 3. Okay, you got that from that equation. Well, if you calculate that out, you'll get 75. And that's going to be right there. See, my gap's getting larger because of that initial velocity, right? Let's do it for 4 seconds. So we'll have 1/2 times 10 times 4 squared plus 10 times 4. Sorry, that's a 4 squared, if you can see that. Let me rewrite it. That's 4 squared plus 10 times 4. That's going to be equal to 120. So 120. And finally, if you did for the 5th second, and I'm kind of running out of room here on this sheet, if you do it for the 5th second, I'll just put it up here. So the delta x for the 5th second, 1/2 times 10 times 5 squared plus 10 times 5. Okay, when you do all that, you get 175. This is pretty remarkable, really. Let me kind of scroll back up a little bit so we can see this. So 175. So this is pretty remarkable here. So without that initial velocity, the car was at 125 meters. So in 5 seconds, how far did the car travel? 125. But with the same acceleration we had before, just adding that initial velocity that the car had, we end up then at 175. So we end up 50 meters further, which would be 10 times 5. 50 meters further just because you anticipated the light. You're much farther down the road than somebody who stopped at the stoplight and then moved with an initial velocity of 0 from the get-go. That's pretty remarkable, isn't it? You know, and again, another way to look at this would be to use kind of a motion map, right? So, and I can draw it kind of underneath there. There was 0. And at 1 second, we're at 15. 2 seconds, we're at 40. 3 seconds, 75. And then 120. And finally, we're at 175, right? So this would represent the car with an initial velocity, right? This is the car that blew through that light with an initial speed. The car that just was accelerating with a VI of 0 only got this far, right? 125. So there's your gap right there. That extra distance or displacement is based on this VI. So we've got to really be careful of this VI here, because it can really make your car go further. And because of that, we had to change your how far equation. So make sure you got this down, because this really represents the full, complete how far equation. All right, so this ends page 4. We'll talk to you later, guys. Bye now.